Hey Phys2 Kids, Campbell here. In our third video on circuits, we're going to talk about the factors that affect the resistance in the circuit. We're also going to talk about power and brightness in bulbs. Now, in our last video, we talked about how current is inversely proportional to resistance. So the resistance is what hampers the charge's ability to flow in a circuit. So it reduces, the higher the resistance is, the more current is reduced in a circuit. We're going to talk some more about what affects the resistance in a circuit. Now, resistance is measured in ohms, which is that nice little horseshoe looking thing. It's an omega. And it's really a property of a device. It's not a variable that can be changed. It's set by how I configure the device. Now, resistors actually have benefits. It's not like, I don't want resistance in a circuit. Some of the devices we use to heat things, like toasters, defrosters on our car window, hair dryers, those have resistors that heat up, and the electrical energy gets converted into thermal energy, and therefore we can, make toast. They're also present in electronic devices, because there's certain devices, certain like bulbs and stuff, that can only handle so much current and voltage. And so resistors help to reduce the amount of current and voltage in a circuit. We're going to be working with resistors that actually look like the resistors in this picture here. They have colored bands on them to indicate what the resistance is, and that's what's inside of the resistor. Like I said, it's a property of a device. It's not something we can change unless we physically change the resistor. Let's talk about some factors that affect resistance. One is the material the wire is made out of, or whatever the material is made out of that we're running current through. Things that are good conductors have very low resistances. In fact, it's called resistivity, that property of the material. It's symbolized by the symbol ρ. But it's a characteristic of a material, so we can go and look them up. Gold has a very low resistance. Copper does too, not quite as low as gold, but gold would be expensive to put in your house. And then you can see that things that are not metals, notice how high their resistances are, including your skin. Although that doesn't mean you can't get shocked. But the property of the material that we use to make our resistors, is one of the things that affects the resistance. Another thing that affects resistance is temperature. And temperature actually is a little counterintuitive, because you would think that, well, if I increase the temperature of material, right, the molecules are moving faster. But that's not just the electrons. It's the protons and neutrons too. So actually lower temperatures are better for resistance. So if I want to lower resistance, I want to lower the temperature. And think about it like this. Say you're an electron and you want to cross a room. And if it's cold, then all the other molecules, all the other people in the room are not moving. Right? That's easier to get across the room. So traveling across the wire. But if it's warm, the molecules are moving faster. It's like the people in the room are all moving around. So now trying to get across the room is difficult, because you got to weave in and out of people. So the lower the temperature, the lower the resistance. And that's because resistivity, this resistivity value we just talked about, is dependent on temperature. And in fact, the resistivity of a metal, that value that we looked at, is set for a temperature, and it goes up when the temperature goes up, except in semiconductors. Semiconductors, the value actually decreases, but that's a special circumstance. Normally, if temperature goes up, then the resistance goes up. Now, just FYI, resistivity and conductivity are very related to each other. In fact, they're kind of the inverses of each other. Another thing that affects resistance is the wire diameter and length. So if you can imagine, a larger diameter will have a lower resistance, because I get more electrons through. There's more area for the electrons to move through, like getting through a larger doorway. With a bunch of people, that's easier. With a small doorway, right, you have to go one at a time. Also, the length of the wire is important. So shorter wires have lower resistances, because the current doesn't have to go as far. I like to kind of think of this in terms of straws. If we think of a wire like a pipe, the straw that's the skinniest is harder to move air through, or liquid. So for example, if I blow in this big straw, Doesn't really resist the flow of air. But if I blow air through this straw, it's harder to blow. There's more resistance to the flow of air. And if I make the straw even twice as long, then it's really hard to blow the air through. So you can kind of think of straws like wires. Bigger straws have lower resistances. Longer straws have higher resistances. Now, if we want to look at it from an equation standpoint, the resistance of a wire is directly proportional to its length. Higher resistance, longer wire. Directly proportional to the resistivity, higher resistivities, higher resistances. And inversely proportional to the cross-sectional area. So the bigger the diameter of my wire, the lower the resistance. By the way, resistivity, I didn't mention this on the slide before. Resistivity, that symbol rho, the unit for it is an ohm meter. That's how we get the ohm in the resistance, ohm. So let's do some math here. What length of copper wire is required to produce a 4 milliohm, oh, that should be a little m, not a big M, that's not mega ohm, milliohm resistor. Assume the diameter of the wire is 1 millimeter and the resistivity of copper is 1.72 times 10 to the negative 8 ohm meters. Well, what do we got to do first? We know what the resistance is. We have a diameter of 1 millimeter. We want to find length. Well, the first thing we need to do is find out the cross-sectional area of the wire. All right, so cross-sectional area, pi d squared over 4, or pi r squared. So first, and make sure you're working in meters. So our area is 7.85 times 10 to the negative 7th meters squared. So make sure you work in meters, because notice that resistivity is ohm meters. Now we can plug this into our resistance equation. We got to do some rearranging. We have the resistance, that 4 milliohms. We're going to multiply that by this area and divide by the resistivity value of copper to get length. When we do that, our length is 0.183 meters. All right, let's move on to power. Electric power is the rate at which work is done. If you remember power from AP Physics 1, right? Power is the rate at which work is done. Or in this case, we're talking about the rate at which electrical energy is expended. Now, so if power, let's think of it this way. If power is work over time, and if you remember from our last unit in electrostatics, we said that work was equal to the charge moving through a voltage difference. Well, we're going to use that equation again because we have this potential difference or this voltage difference that's driving the current. So if I plug that in here, I get Q delta V over T. What is Q over T equal? Do you remember that from our last video, or was that our first video? Current, right, is the amount of charge that passes a point per unit time. Ooh, so that means power, which is work over time, is actually current times voltage, or what I like to call it, PIV. Power is current times voltage, PIV. So that is the equation for calculating power, the rate at which electrical energy is expended. So when I have a resistor, a bulb, any sort of resistor, the power I'm expending, that electrical energy I'm expending, is actually thermal energy, heat. Now, there are many forms of power. If we take Ohm's law and we substitute into our power equation, say I didn't know what voltage was. So here's my power equation, right? Say I didn't know what voltage was. I could, instead of using voltage, I could substitute IR, and then I'd get I squared R. Or say I don't know current. Well, then I could plug in V over R. And so I say there are many forms of power. There's PIV, there's I squared R if I don't know voltage, or V squared over R. Sometimes these are handy other forms because sometimes you don't know both the current and the voltage. You may know one, like you know the voltage of the battery, you know the resistance value of the resistor, so you could find out the power using voltage and resistance. So sometimes these other forms are handy. Let's do some calculations. I want you to pause the video and see if you can calculate out the power and the resistance in these two equations. Well, in our first one, it's straight PIV. Take 120 volts times 9 amps and you get 1,080 watts. So that's how much power this tool is putting out. What about this heater? It's drawing 10 amps of current. What's the resistance in order to produce 500 watts? Well, this time I want to use the power is I squared R equation. And so I take my 500 and I divide by 10 squared or 100 and I get 5 ohms. That's actually a pretty big resistor. You'll see when we start working in lab. All right, last thing I want to talk about is power and brightness in bulbs. When you are asked about brightness, what you're really being asked about is what is the power output of a bulb? Now, when you go to the store and you buy a bulb, and I have 2 different bulbs here, they're rated for a certain power output. So when you go to the store, you buy a 60 watt bulb, which happens to be this little white bulb, a 100 watt bulb, a 40 watt bulb. This is actually a 40 watt bulb. So size doesn't matter of the bulb. But we have different wattages based off what kind of light fixtures we're running. Now, the thing is, when the manufacturers make these bulbs, they have to make that power output for a specific voltage. Now, your homes, if everything is wired properly, your homes, each of your outlets, like each of your lights, is delivering 120 volts. So if I plug in this light bulb, and I don't know if you can see that, where it says 60 watts for 120 volts, it will deliver 60 watts. Now, the thing is remember, power is current times voltage. So if maybe your fixture is wired wrong, maybe it won't deliver that 120 volts. And if it doesn't, then the power output is not going to be 60 watts. So all the manufacturer can do is put a specific resistor in a bulb. So if I wanted this to be a 60 watt bulb for 120 volts, right, we could use the V squared over R. So I could take the power, say that's 60, divide by my V squared, 120 squared, and I would determine what resistor to put in this bulb. But that's all I can do. So I can go to my shelf and pull a resistor off and put it in my bulb and then sell it to you. But if the bulb doesn't operate under the designated specifications, that 120 volts, you are not going to get 60 watts. Now, in class, we're going to play a game, How Bright is Your Bulb? And we'll see if you can figure out, if I run these in different configurations, parallel versus series, if you can figure out which bulb is which. So how bright is your bulb? We will find out when I see you in class. So I'll see you in class.